Hi, I'm Mark Barsamian. In this video, I'll start discussing Chapter 10, which is Graphs and Trees. We'll begin with Section 10.1, in which we learn about walks, trails, paths, and circuits. The corresponding reading is from Section 10.1, the first few pages of that section, 677 to 683, the first 5 examples of the section. The corresponding homework is this short assignment of 4 exercises from Section 10.1. Now we'll start with a review of some basic graph definitions from Chapter 1. Chapter 1 was not covered in a video. The book gave nice, straightforward introductions to concepts in that chapter, so I didn't make videos. But we'll review some stuff from that chapter before starting Chapter 10. Then we'll start our discussion of Chapter 10 with the definition of walk, trail, path, and circuit, and then we'll talk briefly about connectedness. So here's the definition of graph from section 1.4. A graph G consists of 2 finite sets, a non-empty set, capital V, of vertices, and a set, capital E, of edges, where each edge is associated with a set consisting of either 1 or 2 vertices called its endpoints. The correspondence from edges to endpoints is called the edge endpoint function. So the edge endpoint function, again, is a correspondence from edges to endpoints. An edge with just one endpoint is called a loop, and 2 or more distinct edges with the same set of endpoints are said to be parallel edges. An edge is said to connect its endpoints, and 2 vertices that are connected by an edge are called adjacent. And a vertex that is the endpoint of a loop is said to be adjacent to itself. An edge is said to be incident on each of its endpoints, and 2 edges incident on the same endpoint are called adjacent edges. A vertex on which no edges are incident is called an isolated vertex. So for example, in this graph G shown, find this. Well, that's the set of vertices, so we just have to make a set that lists the vertices. That's the set of vertices. Question B, find this. Well, that's the set of edges. We just list the edges. So the set of edges is this set containing 10 edges. Now notice in the definition, the set of vertices has to be a non-empty set. So you have to have a vertex for a graph. But the set of edges is not required to be non-empty. So you can have a graph that just consists of vertices with no edges. Let's continue with this example. Find the edge endpoint function. Well, we present this in table form. There's this set of endpoints for each edge. Notice a couple of things. These 2 edges have the same endpoints. That's an example of parallel edges. Another thing to notice is that this edge only has one endpoint, so that's a loop. Also notice that these sets of endpoints are sets, so the order in which the vertices are listed in the sets doesn't matter. I've listed them in alphabetical order, so the vertex with the lower number is listed on the left. But this same set that I've circled, V2, V4, would be the same if I listed it in the other order, V4, V2. Now section 10.1 begins with the introduction of some new terminology. Walk, trail, path, closed walk, circuit, simple circuit. So if G is a graph and little v and little w are vertices in that graph, what's called a walk from v to w is a finite alternating sequence of adjacent vertices and edges of G. That is, a walk has this form. Sequence of characters that represent vertices and edges, where the V's represent vertices and the E's represent edges, and for each number, I from 1 to n, these vertices, V subscript I minus 1 and V subscript I, are the endpoints of edge EI. So for instance, in this sequence of characters, there's a V subscript 0, an E subscript 1, and a V subscript 1. That would mean that vertices V0 and V1 would be the endpoints of edge 1. If they appear in a sequence like that that's representing a walk, then those vertices have to be the endpoints of that edge that they're flanking. There is something called a trivial walk from some vertex to itself that just consists of a vertex, no edges at all. What's called a trail from V to W is a walk from V to W that has this additional property that does not contain a repeated edge. And then what's called a path from V to W is a trail that has the additional property that it does not contain a repeated vertex. So you see that every trail is also a walk, and every path is also a trail, which means that it's also a walk. So these definitions build on each other. What's called a closed walk is a walk that starts and ends at the same vertex. And a circuit is a closed walk that contains at least one edge and does not contain a repeated edge. What's called a simple circuit is a circuit that does not have any other repeated vertex except the first and last. That definition is nicely summarized in this table presented in the book. Summary of the definitions of walk, trail, path, closed walk, circuit, and simple circuit. Here's an example. We're going to return to the graph from the previous example. Our job is to classify the following walks. That is, decide if each is a trail, a path, a closed walk, circuit, simple circuit, or just a walk. The first walk is this. Now we can highlight that in red. So there I've highlighted that walk. Now we have to decide if that's a trail, a path, closed walk, and so forth. Let's go back up and look at the definitions. A trail is a walk that has no repeated edge. Repeated vertices are allowed, and it's allowed to start and stop at the same point. So you see that has no repeated edges, so it is a trail. Now let's go back up and see what other properties it might have. Does it qualify to be a path? Well, in a path, you're not allowed to have a repeated vertex. So that trail is not a path. Is it a closed walk? Well, remember what a closed walk is. A closed walk is a walk that starts and ends at the same vertex. So it's not a closed walk either. So it's not a path, it's not a closed walk, and it's not a circuit. Let's go on. Question B. Consider this walk. There's a visualization of that walk. Now notice that it uses edge 9 twice. A trail is not allowed to have a repeated edge, so that walk is not a trail, it's not a path, it's also not a closed walk because it doesn't start and stop at the same vertex. So that walk is just a walk. Let's go on. Question C. This walk, V2. Well, let's look at its properties. Notice that it does not have any repeated edges. It does not have any repeated vertices, but that would be okay if it did. It's allowed to start and stop at the same point. It does not contain at least one edge, but that's not a requirement. So that walk has all the properties it needs to be called a trail. Now consider whether that trail is qualified to be called a path. It doesn't have any repeated edges, so that's okay. It doesn't have any repeated vertices, so that's okay. But it does start and stop at the same point, so it can't be called a path. Let's go on. Question D. Look at that string of characters. There are no edges listed, just vertices. Well, the book discusses this, that in some cases you can just have a string of symbols that represent just vertices or just a string of symbols that represent edges, and that in some cases is enough to specify a walk. Let's look at this list of vertices. V5, V2, V3, V4, V4 again, and V5. Well, you realize that there's only one way to have those be part of a walk. So this notation is actually shorthand for this. So that's the full notation for that walk. Now let's see if it is qualified to be called anything else. Does it contain a repeated edge? No, it doesn't, so it is a trail. Does it contain a repeated vertex? Yes, it does. That vertex is repeated. That vertex is repeated. You can look in the lists. V5 appears twice, and V4 appears twice. So it is a walk, and it is a trail, but it's not a path. Let's go back up and look at the other properties. It is a closed walk because it starts and ends at the same vertex. Is it a circuit? Well, that would be a closed walk that contains at least one edge and does not contain a repeated edge. So notice, this contains at least one edge and has no repeated edges. So it is a closed walk and it is a circuit. Let's go back up. The last defined term is a simple circuit. That's a circuit that does not have any other repeated vertex except the very first and last vertex. Well, the first vertex is the last vertex. V5 is repeated, but notice that V4 is also repeated. So it's not a simple circuit because V4 is repeated and it's not the start and stop vertex. So I would call this a circuit. That is, that's the fanciest name. That's the name that has the most properties built into it. So it is a walk, it's a trail, but notice every trail is a walk. So if you say that something is a trail, then it's automatically a walk. And it's a circuit as well. Well, every circuit is a trail. Notice that a circuit is a closed walk. Well, so a closed walk is a walk and it starts and ends at the same vertex. But a closed walk could have a repeated edge. That would mean that it could not be a trail. A trail does not contain a repeated edge. But a circuit is a closed walk that does not contain a repeated edge. So that means a circuit is automatically a trail. And again, a trail is automatically a walk. So all we really need to say about that walk is that it is a circuit. Let's go on. Question E. So here's another walk that's specified by giving a bunch of vertices. So let's start by highlighting these vertices in the graph. So there are the vertices. Now let's draw the edges. Now let's see about the properties. Notice that this has repeated edges and it has repeated vertices. It does start and stop at the same point. Well, the fact that it has a repeated edge means that it's not qualified to be called a trail. Since it's not qualified to be called a trail, it's also not qualified to be called a path. Now, what about closed walk? Repeated edges are allowed. Repeated vertices are allowed. It has to start and stop at the same point. It doesn't have to contain at least one edge. So it has all of those qualifications. Is it a circuit? Well, a circuit's not allowed to have a repeated edge. And so since it's not a circuit, it's not a simple circuit. So the best description of this is a closed walk. It's a walk that's also qualified to be called a closed walk. Again, it's not a trail or a circuit because it has repeated edges. Let's go on. Question F. List of vertices, V2, V5, V1, V2. V2, V5, V1, V2. Well, let's see. Let's draw the edges. Wait a minute. Look at this. It's not clear how we're supposed to get from V1 to V2. This list of vertices is ambiguous. This description there could be this walk or this walk. Those walks are not the same. One has edge E2 at that position, the other has edge E3. So this is not a valid description of a walk. So this is a trick problem. I put this in here to draw attention to the kind of exercise that you have in a couple of your homework problems. You have to consider a string of symbols and decide whether it completely specifies a walk, such as this string of symbols, which is shorthand for a walk, and this string of symbols, which is shorthand for this walk. Those were unambiguous. There's only one walk that could have this list of vertices. But this description of vertices could be the vertices for more than one walk, so this is not a valid description of a walk. Let's go on. Question G. This walk is described by just its edges, E5, E8, E10, E3. So this is shorthand for the following. Notice that that has no repeated edges, no repeated vertices, so that is a path, but it's not a closed walk, it's not a circuit. It's not a closed walk or a circuit because it does not start and stop at the same point. Let's go on. Example 3, consider this graph. How many paths are there from V1 to V4? Now let's remember what paths are. For a path, you're not allowed to have repeated edges or repeated vertices. Well, to make a path from V1 to V4, we have no choice about those edges, but the question is, which edge are we going to use there? So there are going to be three paths, three possibilities. The path that uses this edge, the path that uses this edge, and the path that uses this edge. Question B, how many trails are there from V1 to V4? Well, let's go back and see what a trail is. A trail, you are allowed to have repeated vertices, but not repeated edges. So for instance, a trail could do this. Could just go straight through. So there are those 3 that go straight through. But we could also have trails that do this. Trail like that goes V1 to V2 and then takes edge 2 to get over to V3, takes edge 3 to get back to V2, and takes edge 4 to get back to V3, and then goes on. Notice it has repeated vertices but does not have repeated edges. Well, so the paths that backtrack we can count. We can think of tasks. Task 1 is going to be to choose the edge to get from V2 to V3 the first time. Well, there are 3 choices. Task 2 is going to be to choose which edge you take to get back from V3 to V2. Well, there are going to be 2 choices for that because there are going to be 2 edges that you didn't use in getting over to V3 the first time. And then the third task is going to be to choose the edge for V2 to V3 the second time. But you realize there won't be any choices. The only way to do that is to choose the last remaining edge. So n subscript 3 is going to be the number 1. So the total number of ways, you use the multiplication rule. 6 ways. So there's 6 trails that backtrack. So the total number of trails using the addition rule, the total number of trails is 9. Let's go on. How many walks are there from V1 to V4? Well, walks, you're allowed to have repeated vertices and repeated edges. So you could go straight through, but you could also do this. You could just keep going back and forth like you forgot stuff at the car, and then you could go on. You could do all sorts of things. So there is an infinite collection of possible walks. I want to talk about subgraphs, connected vertices, and connected graphs. A subgraph is just what it sounds like. A graph H is said to be a subgraph of G if every vertex in H is also a vertex in G, and every edge in H is also an edge in G, and every edge that's in H has the same endpoints as it has in G. Then I want to talk about the definition of connected. To say that 2 vertices are connected means there is a walk from one vertex to the other. To say that a graph is connected means that if you choose any 2 vertices in the graph, there's a walk from one to the other. Now there is a lemma about graphs. If a graph is connected, then any 2 distinct vertices must be connected by a path. And if 2 vertices are part of a circuit and one edge is removed from the circuit, then there will still exist a trail from one vertex to the other. And if the graph G is connected and contains a circuit, then an edge of the circuit can be removed without disconnecting the graph G. Now, that's not going to come up in what we're going to discuss next, so I'm just going to move on. What's called a connected component of a graph is a subgraph of G that's connected and that has this property. No other connected subgraph of G has that graph H as a subgraph and contains vertices or edges that are not in H. So the last example is to find the connected components for the graph shown below. Well, I'm going to highlight them with colors first. So there are the 3 connected components. In fact, I'm just going to leave it like that. Well, that's the end of that example, and that's the end of the video. Thank you.